Hi, hello everybody. So this is the video dealing with section 3.3, properties of logarithms. And we divided this topic into three parts. This is the first part, the definition and expanding of logarithms. Now, this, as some of the topics we've seen before, it's a review from what was covered in Math 119. So this is a review. Shouldn't take long. Um, the definition, so let's go over the definition of logs first of all. So I have here the definition of logs, function, log function, base, and the number or item you're trying to take the log of. And it helps to rewrite the problem in exponential form. And the reason we do that is because exponential forms and the log forms are inverses of each other. Now, what does that mean? It means that when we are, and I'll give you an example with a numerical value, when we are trying to, let's say, take the log of a number, the answer to this question, what is the log of 8 base 2? The answer is an exponent. Okay. And the exponent or the answer is the exponent you have to raise the base to, I'm going to put a question mark here, so that the answer is the number you're trying to take the log of. So this is exactly what you have over here, all right? So the answer to this question, b to the y, is the number you're trying to take the log of. So the answer is going to be y. So in my example here, log of 8 base 2, what is the answer? Well, the answer is the exponent you raised to the power of 2, right, in order to get 8. So if I were to write this in exponential form, the question would be 2 to the x equals 8. And what number do I put here to get 8? Well, obviously, the answer is 3. So log of 8 base 2 is 3. And similarly, I can give you several other examples. For example, how about 525? Log of 25 base 5. So again, the answer is the exponent you have to raise to the base in order to get 25. So obviously the answer is 2 because 5 squared is 25. And it's maybe one more example for you to see. How about log base 7 of 1? So log of 1 base 7. So again, the answer is the exponent. What exponent do I need to put here in order to get 1? Well, obviously, the answer is 0 because 7 to the 0 is 1. Or one last example, log base 3 of 3. Right? The answer is the exponent that goes here in order to get 3. So obviously, the answer is 1 because 3 to the 1 is 1. So again, this is a review. Okay, if you need extra information on the properties of logs, or these basic definitions of logs, you can take a look at your notes from Math 119 or just do a check online and see some more examples. Now, the important thing about the log is that the base b right here has to be a value greater than 0, meaning positive, but not 1. Okay, so this is a requirement. Now, in addition to the definition of logs that I gave you some examples that you saw here, we have the 3 basic properties. And so we've covered this before in Math 119, and here I go quickly. So the log of a product is the sum of the two logs. The log of a ratio is the difference of two logs, of the two logs. And the log of a power, notice that the power P here, whatever this number is, goes and multiply the front of the log. So the log of a power becomes the product of the power of the exponent and the remaining log. So we need those three properties when we are doing computations with logs. So the computations will either be expanding logs, which we're covering in this section, or condensing logs, or solving log equations. Okay, for now, we're going to just take a look at expanding logs. So the concept of expanding logs is the following. I am giving a log of a single expression, as you can see here in both cases, and our goal is to apply these properties, either the product, the quotient, or the power property, and expand the log so that at the end, I am left with multiple log expressions, two or more. All right, so let's do that. Again, this is a review from Math 119. So notice in example A, so again, this is taken from the book, so you can check the steps in more detail if you want to. I am giving a generic base B. It could be a number. In this case, it's a variable, and it's just perfectly fine. Okay, so log base B, and at first, I can see that I have a product of two things here, two terms, so I'm going to apply the product rule. So the product rule says the log of the product is the log of the sum of the two expressions. So this is going to be log base b x squared plus log base b of square root of y. Now, in the properties of logs, we don't have anything that deals with radicals. So anything with a radical has to be converted to an exponential form. So you have to remember how to convert from radical form, which is this, to exponential form, which is this. So whatever the index of the radical is, it becomes the denominator, and the power to the radicand becomes the numerator. So again, this is a review. So this expression here, I'm going to have to write log base b x squared plus log base b of y to the 1, and the square root has an index of 2. So anytime the index is not visible, is 2. So now I have the log expression a little bit simplified, and now, and only now, I can apply the power rule. So the power rule is always applied last, okay, if there's a power to be applied. So in the first case, the 2 goes to the front of the log. So this is going to be 2 log base b of x plus, and the 1/2 likewise goes to the front of the log base b of y. And this is my final answer. So I started out with a single log expression, and I ended up with 2. Okay? And my final log expression cannot have any exponent other than 1 in those variables. All right, so that's the first example. Let's take a look at the second example. Now, in the second example, I do have a base. So immediately from the start, I can see that I have a ratio, and I am going to apply the second property, the quotient rule. So I'm going to have log base 6 of cubic x minus log base 6 of 36 y to the fourth. All right, so, and my next step is I can see here that I have a product. So I'm going to apply the product rule in the second log expression. So the first one is going to stay the same for now, and eventually I'm going to change the radical form into exponential form, and I'm going to apply the product rule right here. But be very careful because there's a minus, so you need to open parentheses or bracket, and you're going to have log base 6 of 36 plus log base 6 of y4. And now, right, there's an invisible one. This -1 is going to be distributed here and there. So I will end up with log base 6 of cubic x minus log base 6, 36, minus, right, -1 times a +1 is negative, log base 6 of y4. Okay, so my next step is I am going to convert this to exponential form, and I am going to simplify this. So anytime you have a log expression that can be simplifiable numerically, you must do so. Okay? So just as my conversion here indicates, log base 6 of cubic x would be log base 6 of x to the 1 over 3. Log base 6 of 36 is 2 because 6 square, right? The 2 goes in here. 6 square is 36. And here is I'm not doing anything here yet. Log base 6 of y4. And now my last step is to take care of the exponents using the power rule. So the power rule is always last on expansion. So 1/3 log base 6x minus 2 minus 4 log base 6 of y. And this is my final answer. My final answer, I cannot have any exponents attached to the variables inside the log. Okay? So this is how you apply the properties of logs or the definition to simplify, right? We have to simplify numerically a log expression. So this is my final answer, 1/3 log x base 6 minus 2 minus 4 log base 6 of y. All right, so in the next video, we'll do the second part, which would be the condensing of the logs.